Okay, this video is going to talk about valence shell electron pair repulsion theory and how we use that to determine molecular shapes. Valence shell electron pair repulsion theory, also called VSEPR. So you'll hear that term VSEPR when we're talking about shapes of molecules and how to determine them. Okay, so our definition of the valence shell electron pair repulsion theory is that it's a model that we use to predict the geometry of atoms making up a molecule. And the basis is that we're looking to minimize the electrostatic forces between a molecule's valence electrons around the central atom. And so by minimizing the electrostatic forces between lone pairs of electrons and bonded pairs of electrons, we should be able to come up with shapes describing the molecule as it is, right? And you'll find that when you do this theory, you will find that some things are going to be bent shapes, some things are going to be tetrahedral, and it's all based on the number of items bonded to the central atom, and also the types of things bonded to the central atom, whether they be lone pairs or actual atoms themselves. Okay, so let's talk a little bit about the VSEPR thing and how we can use VSEPR to make predictions on the shape and geometry of bonds and a molecule. And so it's quite simple how it works. Is we're going to look at a simple molecule first to show you how this works. And we're interested in both total electron pairs around a central atom and also the ones that are non-bonding. So we have a total electron pairs, and those will be the ones that both bond and don't bond, so lone pairs. And then we're going to manipulate the ones that are bonding and non-bonding to come up with a geometry. So let's look at that real quick. I'm going to the first one I'm going to do is CH4. So the molecule CH4 is drawn on the lower part of the video here. And so what we're going to do is we're going to look at the electrons around the central atom. So we have to figure out which one is our central atom, and that's pretty self-evident from this one. The way we draw it, our central atom is going to be the carbon. So we're just going to put here A points to the central atom, and B is our bonding atom. It's going to be anything on the outside. So here's one, and here's one. And there's four of them actually, right? So we can go around, but there's four bonding atoms. And then if we had any non-bonding electron pairs, we're going to use an E, and we don't have any in this case. So let's just we don't need that for here. So now let's look at how many things are total electron pairs around the central atom. All right, so we can call this is a pair. This is a pair, this is a pair, and this is a pair. So we have four pair. And then my next question is, how many are bonding? Well, they're all bonding, so there's 1, 2, 3, 4. And if we look on our little chart here, it says for four electron pairs and all of them being bonded, we have a tetrahedral. Tetrahedral arrangement of electrons, and the geometry of the molecule is tetrahedral. So let's just kind of quickly draw one of those here, and I'm going to erase this now because this is a 2D representation of a tetrahedral. Okay, I drew my tetrahedral, and then how this works is this bond here is in the plane of the viewing screen, as is this bond here, and this bond here is coming out of the plane of the viewing screen, and this bond here is going away from the plane of the viewing screen. And then I draw my my things here to indicate all the things, all the it's a tetrahedral. So here's my little tetrahedral bottom, and here's one side here, here's another side here, and then the back side would be back here. Right, and then what we're interested in, what the angle is between this carbon here and these hydrogen here and this hydrogen. So this is the bond angle that we are measuring, right? From hydrogen to the hydrogen through the carbon, and that's going to be 109.5 degrees, right? And if you'll find that if you measure from here to here, and if you measure the same thing from here to here, and then this one also from here to there, they're all going to be 109.5. So that's how we used it for a simple one. Let's look at one a little bit more complicated. Okay, so let's look at water, right? So here's my dot diagram, or Lewis structure for water. And I know it's not drawn correctly for, you may know that water's bent, but this isn't the correct geometry for that. But let's use the chart here to help us define what the geometry is. So if you didn't know, you would draw something like this because that makes sense. But let's see how this chart helps us design what the correct geometry is. So again, we're going to do simple counting. How many things are bonded to the central atom? How many electron pairs are around the central atom that either bonding or non-bonding? So here we have 1, 2, 3, 4. So we have 4 pairs of electrons around the central atom. And then how many of them are non-bonding? We have 1 and then 2. So we're going to go in our chart here and find out which ones are this. So we have total electron pairs, 4. And then how many of them are bonding? 2. And how many are non-bonding? 2. So we're going to follow this way over, and it's going to say tetrahedral is our shape of our electrons in the around the central atom. But our angular, it's going to be a bent shape between our bonding atoms. So the way we're going to now write this is going to be different. We're going to actually have to put a bend in here to make this more accurate. So let's do that let's do that below. Okay, so I've drawn everything up now down here, and I'm going to show you why this is bent. So we said it has a tetrahedral, which makes sense because there's four things coming off the oxygen. But now we know that the lone pairs are going to be more repulsive of each other than they are against a bonded pair of electrons. So these electrons pairs are going to push each other away from each other, which is then going to force these bonded pairs of electrons to the hydrogen to push in, and therefore our angle between here is going to be reduced from the 109 that we just did to the 104.5. So it's a slight reduction, but it is considerable amount of reduction. So that angle is going to be 104.5. And remember, we're not looking at bonds between this bond. We're not looking at bonds between here and here or here and here, because it has to be the bond angle, and these aren't really these aren't bonds. These are just lone pairs, right? And this isn't a bond angle because, again, this isn't a bond. This is just a lone pair. So it has to only be between these two things here. So let's look at another one real quick, just to do one more, a little bit more complicated, and we're going to look at SF6. Okay, I drew SF6 on the bottom, and again, I haven't drawn the correct structure because I don't know what it is, but I'm going to use my chart here to help me out. So let's do the quick thing here. We're going to look at the center atom, which is our sulfur, and we're going to count the total pairs of electrons around the central atom. All right, so 1, 2, 3, 4, 5, 6. So there's six pairs of electrons around this central atom. And then we're going to look at how many are bonding pairs, and we have 1, 2, 3, 4, 5, 6. Okay, so we need to find the thing on the chart here that has 6 and 6, and so we're going to go down here, and it says 6 electron pairs, 6 of them are bonding, so we have octahedral, and it actually gives me the example of SF6. So let me now rearrange these atoms here into an octahedral shape so that you can see what it looks like. Okay, I did my best to draw a octahedral, but basically it's a square that's coming in and out of the plane of the paper, and above the square is going to be a fluorine, and then below the square is going to be the fluorine. And if you drew the thing on its side, it would look the same way as it does now, except these would be in the square. These electrons here, this one, and this one would be in the plane, and these would be above and below the plane. So basically, you can think of it as a square on its side, on a square with the angle. I'm trying to draw a better picture of it here, but it would be something like this here, where it's just, each one of these, it's a four-sided pyramid, not back to back. All right. So anyway, let's aside from my poor drawing skills, let's comment on what it is. So it's going to be octahedral, and that's kind of what it's going to look like. So that'll be the final shape of it. So hopefully this was to help you to understand how the set up the VSEPR thing can help you set up what the shape and of the final molecule is, and show you where the atoms are bonded next to bonded relative to each other to form the shape.